All right, welcome to video 3 in the Uniform Circular Motion unit. This video is going to talk about the math of the unit. And so I've got 6 problems in this video, ranging from all different types of difficulty levels. And so make sure that you are not content with these 6, but use these as a guide and as a starting point to your worksheets and your practice. So without further ado, let's go and get started. In this sample problem number 1, it says a 900 kilogram car moving at 10 meters per second takes a turn around a circle with a radius of 25 meters. Determine the acceleration and the net force acting upon the car. All right, just so you know, this is probably a level 1 problem. This is definitely probably the most basic and simplistic problem you'll get in this unit. And so let's make sure we know how to do it so that way we have a good basis and foundation. So when you're looking at these problems, especially when you're first starting, it's a good idea to do what I call analyzing the problem. And what that means is write out your information that's given to you in terms of its variable form. So when I read it has a 900 kilogram car, I'm going to write mass is 900 kilograms. That way when I go to look at equations, I'll know, okay, mass is included or could potentially be included. Next thing I know is that it's moving at 10 meters per second. That is a velocity. And then it's taking a turn around a circle with a radius of 25 meters. All right, it's asking for what is the acceleration and what is the net force. Now, since it's moving in a circle, I know that it's talking specifically about centripetal acceleration and centripetal force. Okay, so centripetal acceleration is found by taking v squared over r. And so my velocity is 10 meters per second. We're going to square that, and we're going to divide that by the radius, which is 25 meters. And so we end up getting 10 squared is 100 divided by 25, and that gives me 4, and then meters per second squared is the units. Acceleration still has the units of meters per second squared. Now for the second part, it's asking for the centripetal force. You could do this one of 2 ways. You could either recall from the previous video and say, all right, centripetal force I know is mass times velocity squared over r, and plug in your information. Or you can identify and say, hey, isn't velocity squared over r just the same thing as centripetal acceleration that we found in the previous problem? And so really, remember, this is just Newton's second law for circles. And so all I'm going to do is I'm just going to take 900 kilograms, which is the mass, and I'm going to multiply that by the centripetal acceleration I found in the previous problem, which is 4 meters per second squared. And if I multiply all that together, I end up getting 3,600, and then the units is kilogram meter per second squared, or remember, that is a Newton. And I also know it's a Newton because I just solved for a force. All forces in physics are measured in newtons. All right, let's take a look at problem number 2. A 95 kilogram halfback makes a turn on the football field. The halfback sweeps out a path that is a portion of a circle with a radius of 12 meters. The halfback makes a quarter turn of a circle around the circle in 2.1 seconds. Determine the speed, acceleration, and net force acting upon the halfback. All right, let's do some analyzing of the problem. I know the mass of the football player is 95 kilograms. I know the radius is 12 meters. And then, interesting, it gives us some weird information. It says the halfback makes a quarter of a turn around the circle in 2.1 seconds. So let's imagine this a little bit. So we're told that there's this circle that has this radius of 12 meters, but the football player doesn't travel the whole circle. He only travels a quarter of it. Okay, it says a portion of the circle, and later on it tells us he moves a quarter of a turn in 2.1 seconds. So you can think he's maybe doing something like this. Okay, just like that. All right, and so he's doing that in 2.1 seconds. Now, if it's a perfect circle, which, you know, the problem is stating that, then if 2.1 seconds is the time it takes to go a fourth of the way, then it takes him 4.2 to go halfway, 6.3 to go 3/4 of the way, and then finally 8.4 seconds total to go all the way around. And remember, the time it takes to go all the way around a circle is the period. And so the period is not 2.1, but it's 8.4 seconds. All right, so now that we have all of our information, let's solve. The first thing we need to solve for is the speed, and that's found by taking 2 pi r over the period. And so that's going to be 2 pi times 12 meters divided by the period, which is 8.4. And so when we multiply that out, and by the way, in physics, we always multiply the pi out. We never leave pi in our answer. We are going to end up getting his speed is approximately 8.976 meters per second. And you probably could have rounded that maybe to 8.98, but that's fine. All right, the second thing it wants us to do is to solve for the acceleration. Now that we know what the speed is, we can do the speed, which is 8.976, square that, and then divide by the radius of 12. And when I do that, I end up getting the acceleration is 6.71 meters per second squared. And then finally, to solve for centripetal force, that's just going to be my mass times my centripetal acceleration that I found in the previous problem. And so the mass, which is 95 kilograms, times the acceleration of 6.71 meters per second squared, that's going to give me my centripetal force of approximately 638 newtons. Okay, now let's look at a roller coaster. Roller coaster problems are just classic circular motion physics problems, and so we'll be seeing a lot of those. And so let's look at this one. Analytical, which is pretty clever. Analytical is riding on the Demon at Great America, which is the Six Flags in Chicago. Anna experiences a downward acceleration of 15.6 meters per second squared at the top of the loop, and an upward acceleration of 26.3 meters per second squared at the bottom of the loop. Use Newton's second law to determine the normal force acting upon Anna's 864 kilogram roller coaster car. So, for every circular motion problem, unless it's a plug and chug problem like the previous two, for every circular motion problem, it is so important that you always start out doing the same two things. The first thing is we need to draw a force diagram that's with the situation. So what's going on here? Anna is going through a roller coaster loop. And so it looks something like this. And there are two places we are supposed to analyze, the top and the bottom. Okay, so let's draw the force diagram for the top. At the top, force gravity is facing down, and force normal is also facing down. Remember from the previous video, we talked about that because the track is up top. At the bottom of the loop, force gravity is still pointing down, but force normal is pointing up. And remember, I know that force normal has to be greater than force gravity because the net force or the centripetal force has to point towards the center of the circle. Now the second thing, that's the first most important thing, draw your force diagram. Very, very important. The second thing that's equally important is to make sure that you write out your sum of the forces equation. So for the top, my sum of the forces, which is centripetal force, is equal to gravity and normal. And since they both face the center of the circle, they're both positive. Force gravity plus force normal. And it doesn't matter if you put gravity first or normal first, it doesn't matter, so long as you have them both. For the bottom part of the loop, it's still going to be the same two forces, but normal is the positive one, and gravity is the negative one, since it doesn't face the center of the circle. That's very important that you do that. That's extremely important. Now that we have those two things, now we can solve the problem. Before we start, I want to remind you of something that we learned in first semester. We learned in first semester that your normal force is also referred to as your apparent weight. So what that means is if you feel your normal body weight, like right now you're probably sitting in a chair watching this video, you feel your normal body weight. You don't feel like you're, getting heavier or lighter. You feel your normal body weight. And so that is when your force normal is equal to your force gravity. The reason why you even feel your body weight right now is because of the chair pushing up on you. And since you're in equilibrium, because you're not accelerating up or down, they're equal to each other. Now, if you feel lighter, like when you're on a roller coaster and you feel lighter at certain points, this is when your force normal is less than force gravity. And then if you feel heavier, this is when your force normal is greater than gravity. And so we're going to look at this numerically, but I want you to think about moments in roller coasters or rides where you've ever felt lighter or heavier than normal. That's kind of like when you get that feeling in your stomach when you're riding through rides. And so let's look at Anna at the top of the loop. We're told that when she's at the top of the loop, she is experiencing a downward acceleration of 15.6 meters per second squared. And from that information, we want to determine what is her normal force. All right, so let's go ahead and do that. we're going to use this equation that we wrote out right here. Try to move all that. The force centripetal equals force gravity plus force normal. So force centripetal, remember, is the same thing as mv squared over r. That's the same thing as centripetal force. That is equal to force gravity plus force normal. Okay, so the only thing I did differently from left to right is I just changed force centripetal into what we knew it was equal to, which is mv squared over r. Now let's plug in the values that I know. All right, so the mass is the 864 kilogram roller coaster. Now, you could be sitting here saying, wait, I don't know what the velocity is or the radius is, but you don't need to know, because remember, what is velocity squared over r? It's acceleration, and we know that the acceleration is 15.6. So that's going to go here, times 15.6. And so that is equal to, and I didn't leave myself much space here. Let me see if I can move this. Okay, I'm just moving this up. Actually, I'll move it right here. There we go. Okay, so that is equal to the force gravity of the car, which force gravity of the 864 kilogram roller coaster car is just the mass times 10. And so force gravity is going to be 8,640 newtons, and then plus force normal. My normal is what I'm solving for. Okay, so let's go ahead and do that. When I do 864 times 15.6, I end up getting 13,478.4. That's equal to 8,640 plus force normal. If I subtract 8,640 from both sides, I end up getting that my force normal is going to be equal to 4,838 newtons. So when Anna is at the top of the loop, her normal force is 4,838. Notice that the normal force is less than the force gravity. So remember, when normal force is less than force gravity, you feel lighter. So if you've ever ridden on a roller coaster and gone through a loop, kind of recall, how did you feel at the top of a loop? You usually feel lighter. And that's because you're kind of lifting out of your seat a little bit because you're upside down. Now let's take a look at the bottom of the loop. We're told that when she gets to the bottom of the loop, let me scroll up a little bit, she experiences an acceleration of 26.3 meters per second squared at the bottom of the loop. Okay, so we have our equation right here that we wrote for at the bottom of the loop. Force centripetal is equal to force normal plus negative force gravity. I'm going to rewrite that as mv squared over r equals force normal, and then plus a negative is just minus force gravity. Now let's go ahead and plug in my information. All right, the 864 kilogram car times, remember, v squared over r is just acceleration, so I'm going to times that by my acceleration, which is 26.3 meters per second squared, and that's equal to force normal, which is what I'm solving for, minus force gravity, which is still the 8,640. See, the gravity of the car is not changing. It's always 8,640. If I do 864 times the 26.3, I end up getting on the left side 22,723.2 newtons, and that's equal to force normal minus 8,640. And then in order to get force normal by itself, I'm going to add 8,640 to both sides. And that ends up getting me my force normal is equal to 31,363 newtons. Now, when you look at this force normal compared to your force gravity, much, much, much greater. And so remember from above, when your force normal is greater than your force gravity, you feel heavier. And once again, think back from experience. Maybe you need to take a trip to castles and coasters to recall some of this. But when you're at the bottom of a loop and you're coming out of the loop, you feel very, very, very heavy. You don't feel your normal body weight. And that is why, because your normal is greater than your gravity. All right, what I would like you to do right now is I'd like you to pause the video, and I just want to see if you could use our previous example with the roller coaster. I want you to see if you could solve these two problems. And then go ahead and click play to reveal the answers. All right, I'm going to take a guess and assume that most of you probably had a little bit of trouble. You may have gotten the force diagram, which with force normal up and force gravity down. Notice that normal is larger because it has to face the center of the circle, which would be this dotted line right here. you may have gotten the force, some of the forces equation right, which is force normal plus negative force gravity. But then you had a little bit of trouble with this whole going so fast to feel twice your body weight. Remember, your force normal is what makes you feel your body weight, not your force gravity. So if you notice that I went from the equation to the much more in-depth equation, and then I started plugging in numbers. The mass is 65. The velocity is what I'm solving for. 17 is the radius. But then when I went on the right side, for force normal and force gravity, if your gravity does not change. So the man that's 65 kilograms, his gravity is 650. That never changes. However, if he's feeling twice his body weight, force normal must be twice force gravity. And so that's how I came up with 1300 for the force normal value. A common mistake students make, and sometimes they get lucky with the numbers, but it's not the correct way, is they think, oh, if I'm feeling twice my body weight, then that means my mass must be 130. That is not correct. Your mass does not change. Remember, mass is a measure of how much matter you have. You don't lose or gain matter when you go through dips and things like that. So do not change your mass. It's your force normal that changes. So let's go ahead and pause the video again and give you another chance to try the second problem. Okay, so looking at the answer for this one, first of all, let's look at the force diagram. Normal is pointing up, gravity is pointing down. Gravity has to be larger in this one because the theoretical circle is below the hill, and so gravity has to be the greater one since it's the one facing the center. So my sum of the forces equation is force centripetal equals force gravity plus negative force normal, which will simplify into mv squared over r equals force gravity minus force normal. Now we start to plug in numbers. The mass is 65 still. However, notice the radius of curvature has changed to 20. We're still solving for v, and that's equal to the force gravity of the man is 65 times 10, or 650. But notice the force normal is 0. And the reason why it's 0 is because I'm asking, what is the fastest speed or max speed he can go before he flies off the hill? I don't know if you've ever driven over a hill very, very, very fast. But sometimes if you go so fast, you almost feel like your car is lifting off the hill, like you're getting a little airborne or a little air between the hill and the car. Well, at that point, when you're going so fast that you're airborne, there is no force normal. And so the only thing keeping your car down is the force of gravity. And so when you're going that fast over a hill, so fast as if to fly off if you were to go any faster, your normal force is 0. And so really centripetal force is just equal to force gravity. And so we solve for velocity, and that ends up being 14.14 meters per second. All right, this last question right here is, it's more of a conceptual question. It's not really a math question. So the question says, a man, 55 kilograms, is going over a hill with a radius of curvature of 20 meters. How fast should he go to be feeling 3 times his body weight? However, the real question is the one in red, and that is, what's wrong with this question? So I'm telling you right now, this is not a question that can be answered, and you would have to explain why. Now, there's 2 ways to go about it. There is a math way, and then there's a conceptual way. Let me show you the math way first, since that makes more sense to students, but then I want to show you the conceptual way, because on tests, you may be asked to explain this in words, and if you don't have the right words, it doesn't matter if you show it with math, you're not actually explaining it. But let's understand the math first. So we have a man going over a hill, and so at the very top of the hill, his force diagram is going to look something like this. Force gravity down, force normal up. Normal is going to be less than gravity, since gravity has to face the center of the circle. And my sum of the forces equation would end up being force gravity plus negative force normal. Okay, so if we plug in all of our information here, we get centripetal force is mv squared over r. That's equal to force gravity minus force normal. And so my numbers here become mass is 55 kilograms times velocity squared over the radius is 20. And that is equal to the force gravity of the man is 550. And then minus, now it's saying feeling 3 times his body weight. So if his body weight is 550, then 3 times that is going to be 1650. Now, right away, I'm hoping some of you notice that when you start simplifying stuff, on the left side you get the 55b squared over 20, but on the right side, 550 minus 1650 is going to give you a negative 1100. At this point, if you take it out to its logical mathematical conclusion, you're going to end up having to take the square root of a negative number, which you cannot do. It's impossible. And so mathematically, you cannot solve this problem because you can't take the square root of a negative and get a real number. Now, what if the test asks you not to explain it with math, but have to explain it in words? Here comes the really tough part. So this is the actual written explanation right here that I've put together beforehand to help you out. And it says this: in order for there to be circular motion over a hill, a centripetal force is required. The centripetal force will face down when an object moves over a hill. In order for centripetal force to point down, your force gravity must be greater than force normal. And when force normal is less than gravity, you feel lighter, never heavier. Now, when I ask students to do this problem, it takes them a little bit of time, but most students, if not all students, usually get to the point where they say, hey, when you go over a hill, you can never, ever feel heavy. And so they state that, and I say, okay, good. Why? Why can you never feel heavy? So they think about it a little bit more, and then they get to the conclusion of saying, oh, you can never feel heavy. You are always going to feel lighter on a hill because force of gravity has to be greater than force normal. And I say, great, you're on the right track. That's awesome. You're getting closer. Why? Why does force gravity have to be greater than force normal? The last thing they're missing that they eventually get to is they say, force gravity has to be greater than force normal because centripetal force has to face down. They always forget to add that centripetal force piece in there. And so if you read here in the description, you can see that all three of those things are in the explanation. All right, this concludes the video on the math of the centripetal motion. The last video that we view next will be on universal law of gravitation and how satellites orbit in a circular motion.